our final class in this semester. Although probably most of you may not be doing the analog circuit design, but it will not hurt to have some basic understanding of electronics. Kaiser, could you read the first one?
Solid state in which number of covalent electrons fill a set of states covalent band.
Okay, so for each atom, it has several layers of electrons surrounding the nucleus of the atom. So at the outermost layer, the number of electrons, we call that the valence band, the outermost. Okay, then Komiya, could you read the second one?
At higher energies, a new set of quantum states convection band.
Okay, so if we input the energy to the atom, several electrons will be uplifted, increased to another band, conduction band. Marcel, could you read the third one?
Conduction electron and electron occupies a state in conduction band with charge minus Q.
Okay, so electron is negative charge. So Q is the charge for each electron. So minus means the negative charge for electron. Hugh, could you read the final one?
A hole of vacant electron state near the top of the valence band with charge UE.
Okay, good. So this is positive for hole. Because if we have a minus charge, we must have a positive charge to balance each other. It's like the force and reaction force always exist together. Charge, negative charge, positive charge and negative charge always coexisted. Always. Okay, this is the... Okay, so for silicon, each silicon we have 4 electrons at its outermost. So for each electron we have 1, 2, 3, 4. Silicon 1, 2, 3, 4. Silicon 1, 2, 3, 4. 1, 2, 3, 4. Sorry, silicon 1, 2, 3, 4. And for this, it has 5 electrons. So for this atom, we have, say, 1, 2, 3, 4. So there's 1 extra electron wandering around. So for this arrangement of silicon and this Timothy, maybe, I forgot. But this is, for this atom, it has 5 electrons at its outermost layer. So 8 electrons. Then this layer is stable. So we have 1 extra. So it was kicked out. It was moving around. So this one is a free one to become conductor. And in the opposite, for boron, it has only 3 electrons in its outermost layer. Say 1, 2, 3, and silicon contribute 1, 1, 1, 1. So we don't have 1 more electron to fill in this layer. Then we call this is a positive charge. Then we call this hole. So this is P-type semiconductor, N-type semiconductor. 1 free electron conduction. This it's not easy to call this free, but this is a hole. So one free electron may jump here. So this is also a conductor because it has an empty space to accept electron. Then electron just jump around. You can think that way. But electron jump around means hole jump. So just imagine electron goes this way, then the hole goes this way. So this is P-type semiconductor. Then this is the two semiconductors, P-type and N-type. We can use them to create a diode. Then, okay, we attach P-type semiconductor, N-type semiconductor. So near this region, the electron here, so we have another positive, P-type positive hole, N-type negative electron. So some electron here would move here because electrons were attracted by this positive charge. And some positive charge were attracted to this negative charge. Then, see, in this region, electron left, so we have some positive charge left. And here, holes, the positive charge goes this way, so means positive left, we are left with negative. So we have some positive and negative. So as more positive charges goes this way, more negative charge goes this way. This area becomes more positive. This area becomes more negative. Eventually, no more electron can move this way because although electrons were attracted by this positive charge, but we have negative charge here, they will say, no, don't come here anymore. So eventually, we will reach an equilibrium state. So we call this area. Okay, anyway, so I just use English to explain these two concepts. So this is PN junction here. Any problem? Like, do you understand? Marcel?
Yeah.
Okay. PN junction is a diode. B part. Okay, could you read this one?
The region of P-type material is created in an N-type semiconductor.
Okay, so this is N-type substrate, N-type wafer. It's semiconductor. Then we can put oxide here to become, then we can deposit P-type atoms in this region. So how to create P-type region on a silicon wafer? Ami, how to create P-type region here? Okay. So silicon and which elements can we put here to create P-type semiconductor? There's a slide. P-type and N-type. For N-type, which element did we put into the silicon to create N-type? And in which element did we put to the silicon to create P-type? 2 slides ago. Do you remember the image in your brain? Here, do you know which element do we put into silicon to create p-type?
Boron.
Yes, boron. So we put boron dopants here to create p-type region. Then after that, we put metal. So metal is a contact pad. We can put contact. Okay, this is N-type substrate. N-type, then p-type region. And this is the PN. So PN, what do we call this? Line. PN. PN. 1 slide ago, what's the name for this? PN. You forgot. Hugh.
PN junction.
It has. So, Muslim, do you know what this symbol represents? Diode, yes. So PN diode. So VD is the voltage across this diode. It has some value, maybe usually 6.6 volt or 0.7 volt. So VD is the diode voltage. And this figure represents the charge. So Y coordinate represents the distance at the PN junction. So this is, say, charge density. Okay. Frank, could you read this?
For bias VD positive, large current zero diode in P to N direction.
Okay, thank you. We connect P to positive potential. We connect N to negative potential. Then we could come see this is voltage, the X coordinate voltage. The Y coordinate is the current. Look at here. So if the voltage is larger than 0.7 or 0.6 volt, we are going to make the diode become a conductor. See, conductor, because this is current, this is voltage. So this one means we have very, very high current. As long as the voltage is larger than this 0.6 or 7. And if the voltage is negative, we call this reverse bias. So Kumio, could you read this?
Reverse bias VD negative, their reverse current is small.
Yes. Here is it's not zero. It's a very small value, almost zero. If the voltage applied to the diode is negative. But if the voltage is very, very large, eventually it will become a conductor again, but in the reverse direction. So this is the PN junction diode behavior. Okay, so this one. Juan, could you read the first?
P region is self-function as a resistor.
Okay. So again, N-type substrate, P-type region. So now we have oxide here, oxide here, oxide here, metal, metal. So we have two contact pads. So this one and this one. Remember, PN junction means if we don't have a very large potential across the PN junction, there's no current goes through the PN junction. So if we just put a potential here, voltage, say ground, and the current will go this way. So this is just a wire with resistance. So this is a resistor. So resistor symbol here. And the diode here, PN junction, PN junction. Both Chen, could you read this?
High potential in E region, less positive than in N region. The discharge diode is reverse bias. Very little leaking current flow. The diffuse resistor is junction isolate from the substrate.
Okay, so this is substrate because this is PN junction to say current don't come here. Current just keep go this way. So this is the junction isolated region. So this region is due to the junction. So this region is isolated from this region. They don't love each other. No electrons comes to go through this way. All electrons just go this way. Current go this way. Okay. Any problem so far? Okay. Now things gets more excited. We have semiconductor, P-type or N-type. After that, we connect P-type, N-type together to create diode. Then we can use diode. Also, we can use PN junction to create a resistor. Then after that, we make things more complicated. We have PNP. We have 3 semiconductor. Okay, then Kaiser, could you read? Could you read this?
The N-type substrate in an NPN transistor serves as the collector and has a P plus base region diffused into it, followed by an even more heavily doped N-type emitter labeled as N++ to distinguish its very heavy doping. By reversing all the dopings, a PNP transistor can be built. Circuit symbols for both devices are shown in the figure.
Okay, so we take N-type wafer. Then we put P-type. So P-type, only 1 plus region here. Then after that, we put N++, means doping, but with higher concentration, much higher concentration than this one. So we could create N++ region here. Then this is metal. This is metal. So we have 3 electrodes. We call one is base, one is emitter, one is collector. And this is oxide. So your name, please. It's Steven. What's the purpose of the oxide here?
Insulator.
Okay, isolation, because this is electrode. So 2 electrodes cannot contact each other. It will become shorted. Very high current. The device will be damaged. Okay, oxide. This is the circuit symbol for this device. Base, collector, emitter. We call this one bipolar junction transistor, BJT. Because this is NPN, so we call this NPN transistor. And for this one, if this is P++, N+, P-type, we create PNP, PNP. So look at this arrowhead. if there's a small, so this is VCE positive charge, positive potential, VE positive potential. So if you have very small V positive potential here, so current IC, current IB, current IE, IE equal to current IB plus current IC. If you have small current here, then we will have a large current coming this way. IC equal to beta IB. So IB is a value. It could be 20, it could be 500. So it's a current amplifier. So this is the amplifier. Any problems so far? Kaiser, did you learn this in the past?
Yeah.
In several years, when did you learn this?
In college,
College. Which year? First year, second year?
first year.
First year, you learned this. Okay. Frank, did you learn this?
No, but I just get this image from here.
So IB plus IC equal to IE here. IC collector current equal to beta IB. So this is, say, BE, we have a positive potential, and CB positive potential. So this means current is this. This is current direction. This is electron direction. They are opposite to each other. Kumel, could you read this?
Electrons emitted by the emitter with the BE junction forward bias reach the narrow base region, and after a few are lost recombination in the base, most of the electrons are collected by the collector.
Okay. So remember, this is positive. This is negative. So electrons by the emitter. So electrons goes this way, goes to positive. Some of them just positive, negative, just we have recombination means positive charge, negative charge combine with each other. But most of them keep going. Some of them going this way, and most of them going this way. So electron this way and current this way. Okay. So that is BZT device for the transistor. Another type of transistor is metal oxide semiconductor field effect transistor. So MOS, MET, metal oxide semiconductor field effect transistor. So this is the wafer, P-type wafer. We have oxide, oxide, oxide. So this oxide is very narrow. So we call this gate. So this is the one metal, metal, metal. So this is the, we call this one gate. So this one is gate oxide. And we have source, we have drain. And this is P-type. We have N-type and N-type here, NPN device. So NPN device. So this is drain here, source here, and gate here. And this is the substrate. Substrate here, we have body, electrode body. So this is P-channel device. Steven, what's the purpose of this oxide? Yes. So gate, we apply positive charge and say this is negative, this is ground, positive. Again, it's similar to the PN junction. If the voltage VG larger than Vs, more than 0.7 volt, then this device we will have a lot. So this one will work. VGS greater than 0.7 volt. And you will become an amplifier similar to the BJT device. So this is the operation. Martin, could you read this?
No gate voltage transistor cannot conduct current cutoff region.
Yes. Yeah. If the gate voltage is 0, no way, there's no conduction. So this is the, say, VDD and source grounded and gate. So if there's no gate voltage here, no conduction. Okay, then if there's a gate voltage, we apply some voltage here. And remember, this is oxide, and this is ground. So this is VDD. So you can imagine this is a capacitor. We have one electrode here, one electrode here. So we have oxide between these two electrodes. So we have a capacitor. So positive charge on this electrode, negative charge on this electrode, positive, negative. Okay, here, could you read the first one?
VGS larger than threshold voltage indicate the channel is from conduction categorized.
Yes. So if you have positive charge here, negative charge here, these negative charge, they are electrons. They are ready to conduct. If the driving force is large enough, they will flow to become current. So current, electron may go this way, and current going this way. Kyler, could you read the second one?
N-type channel charge carriers are exclusively of the negative type, as MOSFETs are unipolar devices. Electrons injected from the N plus source region into the channel.
Okay, so this is the supply of electrons. Electrons coming from this source. And you may notice they are not symmetric. So this is positive, this is negative. This is positive, but this is a little bit positive. So we have, say, positive, negative, the electric field is larger here compared to the electric field here. So we have more, say, the N channel here, more than the N channel here. If the positive is large, equal to the positive here, we will have cut off. There's no electron. If the positive VGG is equal to VDD, means there's no electron. It will become this way. But if VDD smaller than VGG, we have some electric field here. Okay? Like, do you follow me? Okay. Again, could you read this?
VGS is larger than the source voltage VT, as VGS is in first transistor for your channel device because the channel wells includes most FAT as voltage could choose resistor.
Yes. Say this is the gate, this is the source. So this is the current. If we increase the gate voltage, then the current will increase too. So like this is the gate, this is the drain, this is the source. If we increase the gate voltage, more electrons will go in this way. So here, do you follow this? Okay. Then this is a voltage controlled resistor. As long as we have voltage current relation, this is a resistor. If we change the gate voltage, the resistance is the slope here. So the slope will be a little bit different. So if we change the voltage, the slope, the resistance will be different. So we call this voltage controlled resistor. Right, do you understand? Okay. Okay, then Ami, could you read this?
When VGS minus VT larger than VDS, N-type inversion layer all along the channel region.
Yes, thank you. So look at this figure. We have a linear region here, and we have a saturation region here. And the x-coordinate is this is drain source VDS, VD minus VS. This is the x-coordinate. Y-coordinate is the current. Then so in this region, VGS minus VT greater than VDS, then we have this linear region, non-saturation region. Means VGS is large enough, so we don't have cutoff. So just imagine, if we are under this condition, if there's no cutoff, means you can keep increase VGG as long as there's no cutoff. If you increase VGG, current will be continue to increase. So which is the linear region? Linear region. But when VD, so if VD greater is VD minus VS smaller than some value, we are in this linear region. But if VD, we increase VD. If you increase VD, then this is VDS. We just think S is the ground. So you can take this as VD, okay? So VD, increase VD till S to some value. Then it becomes this way. If you increase VD till some, it will, then this one will just decrease till this point, cut off. In that area, the current will become some fixed value. Like here. So the current will become constant value. So this is the saturation area. Saturation area, and this is the non-saturation area. Muslim, any problem? Like, could you read this?
When VGS minus VT smaller than VDS, it was a layer at the sources, and but this layer disappears at some point along the channel saturated region.
Yes, means if we increase VD and increase VD till this condition is satisfied, we reach the saturation region, this region. Okay. So those are the introduction of the semiconductor device. Now we need to have mathematical equations to model the transistor behavior. And we have small signal model and large signal model. Means if the signal variation is small, we have some equilibrium point. If we change the value very small away from the equilibrium point, we can use a straight line to model this device, linear behavior. That is small signal model. But if this is equilibrium point, we varies the value a lot, then we cannot use a straight line to model this device behavior. We need to consider the nonlinear response. This is the large signal model. BPAP, do you understand? Okay, so we have a NPN MOS device. This is source is grounded. Gate, we have the gate voltage, VGS, between gate and source. So VGS greater than 0. This is positive, this is ground. This is drain. We have a supply. For all amplifiers, we need to supply the power. So this is power supply to the D. So this is VDS. S is grounded, so VDD greater than 0. And V, the substrate, VDS less than 0. Means VB is more negative than the substrate. Again, could you read this?
Persistence larger signal transfer function extend switch speed for internal circuit application.
Quasi-static. Static, we have static and dynamic. But quasi-static is very close to static, but not static, but just nearly static, quasi-static. Okay. But is the terminology is not important here. This is the large signal model of a semiconductor device. See, you have VDS, you have VDS, means you have something square. So if you have square, it's not linear anymore. Linear is first order only. Second order, nonlinear. So this is the equation for drain current and drain voltage. And mu A is the mobility. This is gate oxide. Remember, for MOS device, we have gate oxide. We have a capacitor layer. And W is the width. You can think the drain area the N channel. So we have the length of N channel and W, width of the N channel. You can think it this way. And VGS, gate voltage, the threshold voltage, VDS. And this is the gate oxide equation. So this is permittivity. This is the thickness. So the unit for this one, epsilon A divided by T, but now we take the electron area 1, value as 1. So A equal to 1, so we use this equation, epsilon divided by T as the oxide, the capacitance. And for oxide, the permittivity of oxide is 3.9 times the vacuum permittivity. And mu n electron mobility. It could be, this is for n device, and for NPN, for PNP, we need to use VP, the whole mobility. See, oxide capacitance per unit area. So we take the electrode as value, area value as is 1. So this is the, at the saturation, the boundary between the linear and the saturation area, there's an angle. So at the angle point, the transition point, VDS equal to VGS minus VT. If VDS is more than this value, it's saturation. But so this is the critical point. So like, if VDS less than VGS minus VT, linear or saturation or linear region. If VDS less than VTS minus VT, is the device in the linear region or in the saturation region? No, linear. So if VDS equal to this value, you can use this equation. You can use this equation to get this saturation current. Please do that. Practice, everyone. And could you please? Okay, thank you. Remember, if the drain voltage increase too large, larger than the VB, VB is the voltage we connected to the bag, the substrate. So if VDS larger than VB, then Kyler, could you read this?
As the drain current rapidly increase, eventually lead to device destruction by thermally induced damage.
Yes. So if we go back to this figure, say this is VB. VB is connected to the substrate. So VBS should be less than 0. So Yeah, this is VB. So did I? Okay. I'll get back to you about this point. VBS less than 0. So this is PN junction. So P is too large. Okay, I'll get back to you about this point. Now is the capacitor. Remember, between gate and the drain, we have an oxide. We call this gate to channel capacitance. And we have, okay, Ami, could you read this one?
Velocity capacitance between gate and source, where the thin oxide and polysilicon gate overlap the source diffusion.
Okay, so we have periodic capacitance, means gate capacitance is there, so we need it. But between the gate and the source, there we have a, because gate is an electrode, source is another electrode. So we have, anyway, we have a capacitance. So that is not what we want. We call this gate periodic capacitance. Again, this is drain, sorry, this is not G, this is DRAIN. So we can get to drain periodic capacitance. And the junction capacitance between the source and the body, and the drain and the body. Between the source and the body, between the drain and the body. Source, body, we have a periodic capacitance. Drain and the body, we have another periodic capacitance. So we have gate to source, body to source, body to drain, gate to drain. We have 4 periodic capacitances. Okay, another capacitances in our device. We need to consider when we model the operation of the device. Okay, now is a small signal model. Remember, Kumil, could you read the first one?
Linearized drain current characteristics about an operating point in saturation region include various capacitors.
Yes. Operating point. We select one point, and we change the current or change the voltage very close to this operating point, but very small change. So in that case, we can use a linearized model. And Hugh, could you read the second one?
GM/VGS capture the decrease in drain current with VGS.
Yes, okay. So we use this model, GM/VGS. So this is the drain current. So this is VGS. Remember, gate to source. This is the voltage. If we increase this voltage, then the drain current will be increased. And we use this model. This is the controlled current source by this VGS value. And GM is the proportional constant. So GM VGS is the current goes through from the drain. This is the drain to the source. This is source. Drain to source, we have this value, GM VGS. Kumil, could you read this?
GMB VBS captures the increase in drain current with PBS. Normally VBS is a constant, therefore VBS is equal to 0.
Okay, So we have this value V and VBS to model this behavior. If we have increase in drain current with VBS, if you increase VBS, you increase the current from the drain to the source. So this is the model. Sometimes we ignore this one. Sometimes we include this one. All the models, we don't need exact models. We use the model to understand the circuit behavior. So all these models do not need to be very accurate. Sometimes, without considering this, we will understand the system behavior. We know how to change the capacitance or resistance to know what the circuit will behave. So, but sometimes if you ignore this one, it will lead you to wrong conclusion. So you need experience. You need to read a lot of circuits. You need to do a lot of modeling. Experience help you to make the right decision. Ami, could you read this one?
Calculate small signal input-output characteristic as a linear amplifier when passed to suit for operating point.
Yeah, this is the small signal analysis. Remember, we have positive capacitance between gate and source, between gate and the body, between drain and the body, CDB, between source and the body, CSB, CDB, VGS, VBS. So when you draw the circuit model, you can draw we have capacitance here, and capacitance here, and capacitance here, capacitance here. If this is grounded, if this is not grounded, you can draw this one to the ground. If this one, but anyway, because this one is ground already. So yeah, you can practice this one if you need to do the circuit simulation. But for mechanical engineer, it's good to know what's going on. Maybe you don't need to do the detailed modeling, but it won't hurt you to understand something about this. Okay, again, gate, drain, we have this one. For transfer function, you want to consider, we can ignore length to derive the transfer function. You don't need to consider the frequency effect, but you need to consider the frequency. You need to consider those capacitances. And also this is the resistance to model from drain to the source, this one. Sometimes you don't need to include this one, but sometimes you need to include it. Just depends how much, how large, how accurate you want to model the circuit behavior. Oh, Deepa, could you read this?
A transistor is a passive resistive element. It always dissipates net power. So how can I amplify?
Okay. If transistor, because we have N channel, and electrons flow through it. So it's a resistor. Resistor dissipates power. But how can a transistor be an amplifier? What's your answer? What's your answer? What's your answer? How can transistor be an amplifier? If it has resistor, it dissipates power. Hugh.
It should have lower resistance.
You lower the resistance, still it dissipates power. How can it be an amplifier?
With saturation region.
It's the operation region of the amplifier, but it's not. It didn't answer the question to small voltage in, high voltage out, or small current in, high current out. How can it be this way? Just very simple, straightforward answer. Right. What's your answer? Portrait, what's your answer? We need power supply. We need VDD to supply voltage power to the amplifier, to make amplifier operate. So amplifier, although it amplifies small signal to large signal, but we need to give it voltage, power supply. That's the answer. It's not very, it's just, okay. Aha, could you read this second one?
Output can supply more power than output, and input. This extra power must come from the power supply.
Yes, this is the answer. Okay? Frank, do you understand? Yes. CMOS inverter. So we have a PMOS and NMOS. And PMOS plus NMOS, we create an inverter. So, okay. Kumil, could you read the first one?
N-channel MOSFET driver gate input VIN.
Okay, VE. So from the NMOS, we have the input voltage here connected to the gate of this NMOS. Bipa, could you read the second one?
P-channel MOSFET, load VDD power supply.
Yes. So power supply, top, and this is the bottom. So we usually put power supply at the top, and the ground to the bottom. So VDD is the power supply to the PMOS. Marcin, could you read the third one?
Two drains are connected together at the output, creating a complementary MOS circuit or CMOS.
Okay, so this is the drain of PMOS. This is the drain of NMOS. Two drains are connected together. So PMOS, NMOS. PMOS plus NMOS, we have complementary MOS. Complementary means male, female, they are complementary to each other. Positive, negative, they are complementary to each other. And PMOS, NMOS, they are complementary to each other. So that's why we have the name complementary MOS, CMOS. Okay? Stephen, could you read this one? Okay. If we have a bonding pad here, between the bonding pad and the ground substrate, we have a capacitance of the bonding pad. So CL could be used to model the bonding pad capacitance. Or if there's another circuit here, follow this circuit. So it could be the input to another MOS circuit. CL, the load capacitance, the input capacitance. If we have another circuit here to model the input capacitance. So when you do the pulse simulation, Kaiser, when you do pulse simulation, you put the bonding pad. Did you put the bonding pad to the pulse simulation? No. But when you submit your layout, simulation and the real device, there's a gap. For real device, we need to consider the bonding pad effect. So you need to add bonding pad to try to explain why your simulation result and your measurement result are different. Because there are a lot of things you didn't consider in your H-SPICE simulation. Bonding pad, we have the capacitance. So that's why you need to add bonding pad to your SPICE model. Try to explain why the results are different. Then for that inverter circuit, we want to get the transfer function between the input and output. The current comes through PMOS to NMOS. They are equal because they are, say, the same cable. But we need to put a minus sign here because in the circuit, for NMOS, current from drain to source. But for PMOS, current is from drain to source. So for PMOS, current goes through this way. For NMOS, current through this way. For these two currents to be the same, you need to say minus IDP. IDP this way, minus IDP this way. So minus IDP equal to IDN. Okay? And VE less than minus VTN for NMOS. Cut off. So NMOS minus VTN. Okay, then let's look at the third point. Okay, could you read the third point? This one.
Like we in almost situation, almost trial, rainbow, trial region, linear, and region in.
Okay, so both PMOS and NMOS operate in the triad, the linear region, not the saturation region. So slightly larger VE. So NMOS saturation, PMOS triad, NMOS saturation and PMOS triad. So we have region 1, region 2, region 3. Sorry, I need to recall. So this is region 1. So this is the linear gain region is here. Linear gain region and large VE. So VE, large VE is in this case. And this case is here. VE here. So in this case, NMOS cut off, and VR equal to VDD. So if NMOS is broken, see, NMOS broken. So V out, because you can think there's a resistor here. If there's no current, because VDD minus I times resistance equal to V out. So if I equal to 0, means VDD equal to V out. So VDD, if there's a resistance here, minus I times R equal to V out. So if this one is cut off, means I is 0. There's no current. So means VDD equal to VO. If VDD is 5 volt, VO equal to 5 volt. So this is this region. Here, the y coordinate is V out. V out equal to VDD 5 volt. If V in is very small, V in very small here. Then slightly larger V in. So now if V in increase, then NMOS saturation. Then because PMOS still is in the triad region. If PMOS in the triad region means the current is very small, then both devices, PMOS and MOS, small current. So you can think the both devices are in the triad region. Okay. Then large Vn here, NMOS become triad, and PMOS saturation, but it's still, you can take both of them in the triad region, because if one is in the triad, means current is very small. So it means both devices have very small current. Then the final one is this one. Somewhere between V in small and V in large, we have this linear region. So linear region, very small in input voltage, very small in voltage change. We could increase very large change in the output voltage. So we have large gain area. Gain is delta V out divided by delta V in. If delta V in very small, we have very large V out, so means the gain is very large. But V in is this way, V out is this way. So delta V out divided by delta V in is some negative large value. Okay, so this is the operational principle of this device, the inverter. Then we will use Simulink MATLAB, because for the large signal model, it's a lot of nonlinear equations. We will put those nonlinear equations into MATLAB Simulink to model the system behavior. So this is the Simulink model of MATLAB. We ignored CGD. So for this device, dB, so this is drain and CdB, drain and the bulk. You can think bulk as the ground. Drain bulk, we just put drain bulk and CL together because they are in parallel. So drain bulk capacitance, we just use CL to model it. And for CSB, for source to the bulk, because source is grounded already. So source to ground there's no capacitance. CSB equal to 0. And CGD, this is gate, this is drain. CGD, we ignore CGD. So CL here. So we only consider CL, and we ignore the other capacitances. And for this model, please derive this condition. If we ignore the other capacitances, we only keep CL here. Please derive this one. Thank you. Then for large signal model, we have PMOS large signal model. We have NMOS large signal model. So we have sub-function to model this system behavior. For PMOS, input VSG, and VSG and VSD, the two inputs to the PMOS model. For the NMOS model, VGS, VDS and VDS are the two input models. And the output for PMOS is current output minus IDP. For NMOS, the output is the drain current IDN. So we have PMOS model, NMOS model, but we have this circuit behavior. So dV out dt, this is minus IDP, IDN. So minus IDN, minus IDP plus sign, this is minus. So IDN plus, this is minus. So minus IDN, minus IDP here, and this is the gain times 1 over CL equal to integrator. Integrator is 1 over S. So 1 over S, so this is S V out. So integrator, so this is dV dt equal to V divided by S in frequency domain. So this equation is here, integrator, gain, and this is sum. So these three blocks represent this differential equation. Like, do you understand? Okay, then this is the oscilloscope, just to show the output curve. And this is we use this variable V out. So this is V out. We set the V out to a file or a variable in MATLAB. And for the PMOS, VSG equal to VDD minus VB. VDD minus VB is VSG. VSD equal to VDD minus V out, because VSD equal to VDD minus V out. This is S, this is D. So V out minus, this is V out here to this block. For NMOS, this one, VGS, so this is input VE, is a signal generator, this one. So this VE minus this VGS, and VDS, S is grounded, so VDS equal to V out. So VDS equal to V out. Okay, so we finished the Simulink model of this circuit. So any question, Kaiser? So we will create this model. But before we do that, remember we need to have PMOS subsystem and NMOS subsystem. So this is the NMOS subsystem. For NMOS, remember we have VGS and VDS, the two input. And the one output is IDN. So input ports 1, 2, output ports. So this is the subfunction inside NMOS. So for NMOS, we have the equations. And we know the kappa N value is mu N CR WL is kappa. And kappa P is mu P CR WL is kappa P. So those are the values you need to supply to MATLAB. And for NMOS, so this is the saturation region drain current expression. So this is saturation region drain current expression. This is the triad. This one. So this one is the between triad and the saturation regions. Okay, so this signal, so this is multiplexer. You can get two signal in and get the two signal out. So VDS and VGS get into this MUX. And for triad region, so this function, we put this function here, we put this function here. So we have function 1, function 2. And so this is triad, so we have a switch. Triad region output. So this is the ground potential. We use VGS, VTN. VTN is the constant, the threshold voltage. So this is plus, this is minus. If VGS greater than, we use this one as the control signal. So this one is VGS minus VTN. This is VDS. So this block here is VGS minus VTN minus VDS. So if this is greater than 0, triad. If this is less than 0, saturation. Okay? So this is the control block. It's a switch. Control the switch go this way or this way. Two-way switch. We use this value to control. So triad. If it's triad, get output. If this is saturation, get output. And this one is another switch. VGS minus VTN greater than 0. We have output. If VGS less than VGL, there's no output, cut off. So this is second switch. Kaiser, could you read this?
Use 3 parameters Kn,
Kappa,
kappa and V, Tn and lambda n to implement saturation and triode region equations.
Yeah, you need these 3 parameters for this processing technology. For UAT MEMS, they need to give you what is their VTN, what is their lambda n, what is their kappa n. depends on your fabrication technology. But okay. PMOS subsystem. So output is minus IDP, and input is VSD, VSG. So this is the saturation region equation here. Saturation region. This is tri-arc region here, and two switch to get the output minus IDP. So I don't get to this one. You can. They are similar to the MEMS subsystem. Okay, for the Simulink model, VDD 5 volt, VE is so VDD. So this is VE. VE is a square wave. VE 0 to 5. 0 to, okay, I use 0 to 5. Square wave, VB 3 volt, CL 1 Faraday. Sorry, 1 femto capacitor, 1 femto F, 1 femto Faraday. So this should be lowercase f. Kappa N, kappa P, lambda N, lambda P, VTN, VTP. And I use VB 5 volt to simulate the first one, VB 2 volt to get the second one. Okay, so let's see the Simulink model. So this end file, I put the commands here, and MDL file is the Simulink model file. So 14.19 Simulink. You look tired. So what time is it? It's 2:53. So let's take a break. Let's come back around 3:15. Okay? And camera off, please. Just like you check cell phone. And your frequency just resonate with your cell phone. Without cell phone, you won't feel safe. Without cell phone, you won't feel happy. I don't like cell phones. Open. Download. Figure 1419 MDL. Okay, so remember, PMOS is a subfunction. NMOS is a subfunction. So in Simulink, there are a lot of blocks you can choose from. So we can show the model. Library browser, you'll take some time to, okay. So this library, we just move it around to resize this library. And move it down. In Simulink, usually this one is the commonly used blocks. Commonly used blocks. And the function generator, the math operations. Then for this function, this is a function block. This is summation block. This is constant. So let me double click on this function clock. Okay, we come into the sub-function. And this is input port, and this is the equation. Remember, for this equation, we have input, 2 input, 1 output. So input 1. So U1 is input 1, U2 is input 2. So we have Kp is a constant, VTP constant. We have lambda p constant, U1 and U2. So this one is U1, remember? U1, U2. Color, which one is U1? E1, 2, which one?
Upper.
This one, U1. So this is the equation for triad region. And this one is the equation for saturated region. And this is the switch. Okay, remember, two-way switch, we have one control signal. The criteria for go to the first input, when this input is greater than threshold, and threshold is 0, you can assign your own threshold. And you have 0 crossing detection for this mainland function. So if input greater than 0, threshold 0, we go to this one. See, U2 greater than threshold. So it has 3 operations. You can select if this one, or this one. And this one is the input port. So for input output, signal routing, sinks, source. Okay, this is the source. So source, we have this one. Say this one, you can input. But we just show you how to drag this one and put it to your work window. And this wiring, you can create any wire by using your mouse. And let's take a look at our main function. Figure 19.m, this is the main function. No. I will increase the font size. No. Control plus. Okay. See, initially, V out is 0. It's just an initial value. And VE, VDD 5, VB 3, VTN 1, kappa N 50, lambda N, VTP, KP, lambda P. So these are the input constants. And CL1 Faraday. Okay, stop time 2. And so this command, so this is the Simulink file, .mdl file. So we issue this command to run Simulink. Then we plot the result. T out, V out. But you didn't see T out. Where does it come from? It comes from here. See, start time. This is the variable, start time. You type start time here. So start time here. You define start time. So you need to type your start time, or it could be ABC 1, 2, 3. It's just a variable. Then the V out, this one, because you define output variable, V out. So that's how you can get your result. So that's why you can V out. But T out is the T out. I remember is the system variable, but let me make sure it's system variable. I remember it's a system variable. So we can run this one. Scope here, and scope here. Put it here, and put this one here. Then here. So I just shrink the size. And I type the file name F14 underscore 19, and I run it. Okay, output. So this is the oscilloscope, and this is the output. Okay, because I created this file 25 years ago, and it was MATLAB, very old version. So the legend command, now they modify the legend command. So there's the error message here. It's the legend, say 49. Now they don't accept the 0. They accept the other parameter. So if I delete this one, I run it again. So now there's no error message. Okay. Now the time is 3:29. I set cell phone off the table. Park it. Now it's 3:29. So please, you create this Simulink model. You create this one. You can follow this pattern. Just do it by your own hand. It will help you to familiar with the Simulink. So please, go back and do it. Then 4 p.m., please come back here.